Hello students. Today we will discuss few questions related to 8086 assembly language programs. So let's begin. Suppose DX and BX registers each contain 4-digit packed BCD numbers. Write an 8086 assembly language program that adds the BCD number in DX and BX and stores the result in CX register. The answer should be in valid BCD format. So let us write what are the given things to us. So the first is that we need to store the operands in DX and BX register. So operands should be in DX and BX register. Second, the end result is in CX register. Okay, so stores the result in CX register. So end result in CX register. Now, what can we formulate from this question? So if you read the question properly, it is saying that it contains 4-digit packed BCD numbers. So 4-digit means, so DX and BX can store 16 bits. So 16 bits means 4 digits. So we have to store 2 bytes data in this DX and BX. Alright. And we have to perform an addition. So here it is given add the number, add the BCD number. So we have to perform an addition. Now, which instruction will we use? In the previous video, we have seen AAA, AS, AM, AD, DA, and DAS instruction. So out of them, what will we be using? If you go through the question properly, here it is said that packed BCD numbers. There is no mention of ASCII anywhere. So all those ASCII adjust instructions are out. Now we only have to use DAA instruction because it is asking for adding the BCD numbers, and the answer should be in a valid BCD format. So we'll be using DAA instruction. So if you recollect, in the DAA instruction, the first point was that makes use of packed BCD numbers and converts it to a valid BCD number. And the second point is very important in DAA instruction, that it operates only on AL register. So you have to keep this in mind, and then we have to write our 8086 assembly language program. Let us assume the values of DX and BX register. So content of DX equals to 4567H, and the content of your BX register equals to 1234H. Now based on this, we can write the content of DH register is 4045H, and content of DL register is 67H. So right now we are just formulating how the program will work. So I'm just taking an example, so this will make you clear that how are we going to write your 8086 assembly language program and what instructions we have to use. The content of BH equals to 12H, and content of BL equals to 34H. Now we have already seen here that the DAA operates on AL register. So AL can only store how many bits? 8 bits or 1 byte. So we have to perform addition byte by byte instead of 4567 added with 1234. So what we will be doing is, if we just formulate the process, the first step will be that we have to move either the content of DL to AL or BL to AL and add the other one which is left out. So what I will do is I will move the content of BL to AL, and in the second part I will add the content of AL with content of DL, and this will get stored by default in your AL register. After the addition is done, we have to check whether it is a valid BCD number or not. In order to check that, what we'll be using is, we'll be using DAA instructions. So the third step will be, we'll be using DAA instruction. So once DAA instruction is used, the content of AL will contain a valid BCD number. And in the fourth step, we will store the content in AL into the CX register. So the content of AL will come to CL register. Alright, so I can write the content of AL goes to CL register. Let me just show you the example how it will work on. So the content of BL goes to AL, so now AL contains 34H. Now AL plus DL is AL is 34 and your DL is 67. So 4 plus 7 is 11, and 11 in hexadecimal will be represented as B, and 6 plus 3 is 9. So we'll be getting 9BH. Now if DAA is implemented on this part, that is 9BH, it will check whether it is a valid BCD number or not. Now B, that is the lower nibble, is not a valid BCD number, so what will happen? We will have to add 6 to this. If we add 6, B plus 6 is 11, so I write 1 here and 1 goes to the higher nibble. So higher nibble is 9, 9 added with 1 will give you 10, 10 in hexadecimal is A. So this is A1H. DAA instruction will again check whether this is a valid BCD or not. So if you see the higher nibble is not a valid BCD number, it is A. So what it will do, it will again add 6 to that part. So we'll be adding plus 60H. So if you add plus 60H, 1 plus 0 will give you 1, and A plus 6 will give you 1, 0. So this is 1, 0, 1. But you know that the content of AL is only 8 bits. So 0, 1 will be stored in your BCD format as 4 zeros followed by 3, 0, 1. And this one will not be stored in your AL register because it only can support 8 bits. This will be stored in your carry flag. So I can write the carry flag content is now 1, whereas the content of your AL register is 01H. If you are comfortable with hexadecimal addition, you can very well do this. If not, you can use your calculators. Let me show you by the Windows calculator. In hexadecimal, if we add 34 plus 67, we get 9B. 9B, since B is not a valid BCD, so we added 6. We got A1, and A is not a valid BCD, so we added plus 60. So we got 101. Now this 01H goes to your A register, the most significant digit. That one will go to your carry flag. The step number 4, the content of AL is moved to your CL register because we have to store the end result in your CX register. So I can write that this is the content of the CL register. So we are done with the lower byte. Now let us move to the higher byte. So content of AL added with DH. Now content of AL is the content of BH. So BH contains 12 and DH contains 45. So let us add that. So 12 plus 45, and we also have to include your carry flag. Now carry flag here is 1, so we'll be adding plus 1 to this. So if we add, the final content will be 2 plus 5 plus 1, which gives you 8, and 4 plus 1 is 5, so 58H. Now in our example, we have seen that the carry flag is set to 1, so that is why we are adding 1 here. But there may be certain examples in which the carry flag is not affected and the carry flag is 0, so this will not make any change in the higher byte. Now in order to ensure that the carry flag is 0 initially, what we will do is we will have to initialize CF to be 0. So I have written here already, initialize carry flag equals to 0, for which we will be using the instruction CLC. Okay. Now after this instruction, like add with carry, we will perform a DAA. Now if you see DAA will check whether the lower nibble is a valid BCD or not. It's a valid BCD number. So 5 is also a valid BCD number, which is your higher nibble. So no change will be observed in this case. So this will be the final content of your AL register, and which will be moving to your CH register. So this is what is your step number 8. So the final content of your CX register will be 5801. Now let us perform a decimal addition and we'll check. So if you perform a decimal addition, 4567 plus 1234, we get 5801. If you want to use a calculator, you can use. So I'll go to the decimal, clear, 4567 plus 1234, you get 5801. So our objective has been attained. Now this is just an example I have taken. You can try it with different values. Now let us proceed towards writing your assembly language program. Now we know the process. So let me first initialize your registers. To initialize, we'll be using move dx comma 4567h. You can assume any values. Move dx comma 1234h. Then initialize carry flag equals to 0, so we'll be using CLC instruction. After that, the first step should be content of BL should be moved to AL, so we'll be writing move AL comma BL. After that, AL has to be added with DL, add AL comma DL, then DAA will get executed, so this will complete your first byte. Then in the next step, moving to your fourth step, which is your AL comma CL, so move CL comma AL. After that, we'll be moving to your second byte, so move AH comma BH, sorry, AL comma BH, then ADC AL comma DH. Then we'll be executing DAA instruction, and the final instruction will be move CH comma AL. After that, you can write alt. Okay, so this will stop your program. So this is your 8086 instruction for this question. I'm not writing the comments because this is basically your comments what we have already formulated the process. So this completes your question. Now let us move to the next question. The next question states that multiply the contents of AL by a factor of 5 using shift instructions. Whenever you see this type of question, so we have to understand the property of shift instruction. So I have already told this, the application of shift and rotate instruction. Shift is also used for serial transmission, and it can also be used to multiply like your rotate instruction. So shift instruction, if you are left shifting it, so if it is left shift, then you are doing binary multiplication, and if you are doing right shift, it is binary division. Okay, so binary multiplication means multiplying by a factor of 2. Now let me take a generalized case to make you understand this problem. Suppose the content of AL register is X, right? We need to multiply by a factor of 5. So what will we do is, whenever any factor is given, we should first try expressing this in a factor of 2 or a power of 2. So 5, I can write 5 equals to 2 power 2 plus 2 power 0. So this is basically 2 power 2 plus 1. Now if I multiply this with x, so x into this will give you 5x. So this is basically equals to 5x. So we are getting the objective, that is multiply the contents of AL by a factor of 5. Now from this you can very well understand that 2 power 2 means you have to do left shift by 2 times. So when you do left shift 2 times, it will get multiplied by 2, and in the second left shift it will get multiplied again by 2, so you'll get a power of 4. And if you add with the same content, that is x, so you'll be getting 5x. So I can write here 4x plus x. So let me explain here. Suppose I have taken a backup of the content in BL, so the content of AL is moved to content of BL. So BL is now x. If we do left shift 2 times the content of AL, this will give the value 4 times of AL. Okay. So finally we have to add the content of AL plus the content of your BL. This will give you 5 times that of AL, which is the objective. Let me take another example to make things more clear. Suppose in this question it is given that multiply the contents of AL, instead of 5 it would be suppose 37. So I can write here instead of 5 37. Now how will we proceed? So as I said, the same thing which you have done here, you have expressed 5 as a power of 2, you will be doing that with the case of 37 also. So 37, if I want to write, now I can write this as 32 plus 4 plus 1. So this will be 2 power 5 plus 2 power 2 plus 2 power 0. So 2 power 0, let me just write here 1 because you will just be saving that content 1. Now in this case, suppose the content of AL is X, so you move it to BL as you have done here. So this will act as your this plus 1 later point of time. Then you will be doing 2 times left shift. So if you do 2 times left shift, you will be getting 4x. So this 4x content you can save it in register CL. So if I the content of AL, which is now 4AL after 2 times left shift, this you save it in register CL. After that again you can do how many times? 2 power 3 times, because already you have done 2 power 2 times, so 2 times you have done left shift, so more 3 times if you do left shift, you'll get 2 power 5. So that will be the final content of your AL. So already you are having 32 AL, which is already present in AL. Now 32 AL you will be adding with CL. So CL is already 4AL, and then finally you'll be adding with BL, and this will give you your 37x. So that is the objective of this question. And initial question was by a factor of 5. So let us write a program for this question, starting with move BL comma AL. So we have taken the backup of AL in BL register, so that will act as this one. Then after that we have to do left shift 2 times. So this 2 times will go to which register? Move CL comma 0 to H. So please remember the CL register contains the count, so that is why I have stored move CL comma 0 to H. Then you have to do left shift, so SHL, and that is logical shift, so SHL AL comma CL. So this will do left shift of 2 places of your AL, and after that we have to add the content with your BL, so add AL comma BL. So this will store the final result in your AL register, which will be a factor of 5, what would be the original content of your AL. Now you can very well comment this. We have already understood the process, so you can provide the required comments. Now let us move to the third question. In this question, we have to write an 8086 assembly language program to verify whether an array of 100 bytes contains all elements whose value is FFH. If all the elements are FFH, we have to store 001H in your DX register, else stores 0000H in DX register. For this question, I will not be writing the entire program. I'll give you the hints, and it is your assignment to complete the program and mail it to me. So I just provide the subtle hints for you. So let me explain you the program first. So we have to verify whether an array of 100 byte contains all elements whose value is FFH. So there will be an array which will be stored from physical address. Since physical address is not given, you can consider any offset. So this data will be stored in your data segment. So I am assuming the content of your data segment is 6000H. So you have to initialize data segment. So please remember, the initialization of data segment will not happen directly. You have to move it to AX register and then move to DS register, and let the offset or the starting element of the array be stored in your BX register. So let the starting value be 4000H. Okay. Now this is not a string, it is just an array of numbers. So it is not required that you have to use DS and SI. You can use BX register as your index. Next, if we see here, we have to check whether the value is of all the elements is FF. So how will you compare? So you can store in this value FF in one register, or you can use FF directly in the instruction itself. Now which instruction will you use for checking? So we can use CMP instruction to check whether the value is FF in all the elements or not. Now this has to run for 100 bytes. For one time you have used CMP instruction, so you have to run this in a loop. We have seen the loop instruction has two variants. So one is loop if equal and loop if not equal. So it is up to you to decide which instruction you will be using. This I will not tell you the answer. Please think about this. Just go to the definition of loop equal and loop if not equal, and then decide which instruction will you use. Now if you know that loop instruction will loop that many times, what is the content stored in your CX register? So with this you will get another hint. So CX register content should be what? I can write equal to it should be 100. Now 100, you cannot write 100H because 100H will give you in a hexadecimal value. 100 is in decimal, so in hex if you convert, you'll be getting 64H. So you wrote the count value as 64H, perform the compare instruction, and this whole process you have to either use loop E or loop any. You people think about this, which instruction you'll be using, and accordingly once it comes out of the loop when Cx equals to 0. So if the loop gets completed with Cx equals to 0, that means all the elements in this array is FFH. So you have to check what is the content of your Cx. So if the content of Cx equals to 0, you will be sure that all the elements in the array contains FFH. So you can write here the content of DX register, in that case should be 001H, else that means Cx is non-zero. So this loop will break when the content of Cx is non-zero. So that is why it came out in between, and if that is the case, then the content of your DX register should be 000. So this should be your content of your DX register if it comes out while the Cx is non-zero value. Fine. So with this process, you can try to formulate your 8086 assembly language program and mail the answer to me. With this, we finish your complete 8086 instruction set, that is your unit number 5. In the next video, we'll be moving to unit number 6, which is your 8086 interrupts.